Welcome, and in this new course, quantifying uncertainty in subsurface systems. So here in this course, we'll be treating that problem of uncertainty quantification, and particularly to the Earth Resources Challenge. So in this first introductory slides, I will narrate a little bit about what that challenge is and what the course contents is in the kind of video material that you'll be finding in this GS260 folder. So Earth resources, we're looking here in particularly about subsurface and geological resources. So there are a number of resources that are well known there. So we have, of course, fossil fuels. Oil and gas is still an important energy that will be used in the next several decades. Of course, preferably we would like to transform that energy into more sustainable and environmentally friendly energy. Yet at the same time, we need to still be mindful about the environmental impact of that energy or the optimizing of production of that particular resource. So heat is another source or energy resource, and particularly when you think about the high enthalpy geothermal systems that generates steam, which drives turbines and then produces energy. On the other hand, we can also use low enthalpy systems where we essentially using the groundwater system as a heat exchanger, and this is particularly done at a much smaller scale, for example, than to heat buildings, and it's very popular in Europe right now. Groundwater, obviously, for drinking water will become an obvious and important resource, particularly because of the fact that surface water may be more contaminated. But of course, we also have to be mindful about not contaminating our groundwater system. There's also the issue of competition with food and energy. In particular, of course, the shale production has essentially required a lot of water, not necessarily drinking water, but at least there's a lot of water required there. For mineral resources is becoming increasingly important, of course. So we have the big minerals, metals, copper and iron for infrastructure. If we then go to energy, then we're looking at things like cadmium, lithium, cobalt, and nickel. For devices and fiber optics, we're looking at rare earth elements. And so, again, these are important things that resources that we'll need to get our attention in the future. Then finally, also the subsurface is used as storage. This either is natural gas or CO2, but also water, simply because surface water can evaporate, and so storing water in the subsurface is, which is called aquifer storage and recovery, is becoming an increasing practice. So the word sustainability is used a lot, and here in this course, we're looking more to say the supply side of that question. Can we minimize the environmental impact of resource extraction, and in particular, say, fossil fuels? The other alternative sources do not come with their own problem. For example, for heat extraction, there have been issues related to earthquakes, and there are some really sort of spectacular news that came out in terms of earthquakes that happened in Switzerland and how that affected the geothermal projects. So the same for mining practices. So we like to optimize those practices and minimize, say, the scar we leave behind on the earth. And you could say, well, any resource that's not economical is best left in the ground. Storage, there is a risk of contamination and loss that we have to worry about, and so we have to understand those risks. And possibly the most important resource is the environment. After all, that's where we live in. So scientifically, how do we address this problem of earth resources and its impact on the environment? And what is really needed to start achieving that? Well, I see four areas. There's a need, of course, for fundamental science still. This would require, for example, understanding the various processes that are happening in the subsurface and how they affect our understanding of the resource, or how they affect our understanding of the extraction of the resource. So in terms of geology, understanding the geological processes that have taken place is an important part of that, because that will lead us to building models that reflect much better the geological heterogeneity that's there, and therefore possibly allows us to quantify uncertainty and make optimal decisions. So this fundamental science is something that is ongoing and happens in many departments around the world, in geological department, geophysical department, even physics and material science. In this course, we'll focus more on the predictive models that have been developed from such fundamental science. For example, in multi-phase flow, people have done fundamental science around the pore material and how fluids move through this pore material, and that have been translated into predictive models such as flow simulators that can be used to make predictions at much larger scale. So the predictive models are exactly that, are essentially models that allow to make future predictions. And so these models could be either computer codes or even analytical equations, or possibly even simple sort of scenario understanding. There's no good predictions without any data. Of course, all these models will have to be sort of tuned, calibrated, inverted. There's a whole language there. We'll have to use data. And in the subsurface, we'll see that there's only sort of three types of data, which is either you drill in the subsurface, or you take geophysical measurements, or you create sort of geological understanding. That means using geological expertise to interpret what is being observed. So that will be an important part of this course, is data science. And the second important part of this, last important part of this course, is decision modeling. And of course, it has to do with the fact that we'd like to understand what is the impact of all that we have, the data, predictive models, fundamental science, in actual decision-making situations, because that's where the rubber meets the road ultimately, is how do we make decisions, how do we make informed decisions, and particularly how do we make decisions under uncertainty. To provide you an example of what I meant in the previous slide, let's consider the problem of groundwater management. So in groundwater management, people are still doing fundamental science related to, say, the biogeochemistry of the system. So how does the biological, the geological, and the chemical agents, how are they interacting with each other when we, say, start pumping or when we contaminate the system? So that understanding is a fundamental science that requires laboratory measurements, field measurements that will be needed to generate what comes next, which is the predictive models. So for predictive modeling, there are many types of models that have been developed. ModFlow is one. Other are CrunchFlow, and you talk more about reactive transport in the subsurface. So these models, once we build models, we can do predictions, future behavior of the system. But of course, such predictions would be quite uncertain and possibly even meaningless without having some data. And that's where data science comes in. In the groundwater management, we have many types of data, which is pump data, tracer data. These days, also more increasingly geophysical data. And then, of course, we make certain decisions that are required in management. After all, management is about decision making. And so there we could say, where will we plan our drinking well field? What kind of rates of extractions will we be using? How can we optimize those rates of extractions, etc.? So that's more of a decision optimization problem. So in this course, we'll be dealing with 5 case studies. These are real case studies, will involve real decisions making. And so these will provide you a good overview of how all these elements come together. So there will be one on oil and gas production planning, there will be one in groundwater management, one about the low entropy geothermal systems, one about the environment and remediation, and then one about unconventional resources. So let's talk you through a little bit of these case studies, just to give you a little bit of a flavor of what's going to come and what are the real problems that we are facing in these kind of situations. So here we are in Libya. We have quite a structurally complex system. And this was shown here in the subsurface, and so that leads to because that even though you see here lines being drawn, these lines, they were the faults, are highly uncertain. These are just more conceptual. In reality, we'll use geophysical data to do that, but the problem here is that geophysical data is not of great quality. So that means that the subsurface structures are not well understood. And particularly things like faulting and how faults act when fluids move through them are not well understood. And so that's important. For example, here in the bottom here, we see sort of two situations or scenarios that could happen. One, we have 4 faults where we see that the oil-water contact is sort of very heterogeneous in nature. It's not just a flat oil-water contact, which has to do to the sealing of that fault. And so here, for example, you have another situation where a fault that's possibly not sealing, and here a fault that is partially sealing, which creates this what is called a perch aquifer. And so the production planning, you don't want to be drilling producers in the water. Obviously, the production planning is going to be highly affected by understanding the system, which is uncertain. So what kind of decisions does manager make in the production planning? There are a number of type of decisions, and I'll just illustrate 3 of them. For example, this is in the case where we're already producing the reservoir. So we're not in the case where we are appraising the reservoir. So when we produce a reservoir, in particular when we inject water into the subsurface to drive oil towards producers, we have to worry about injection efficiency. It means how much water do we allocate to what injector. So that's basically a quantity or a rate that needs to be determined. So after a while, that doesn't cut it anymore, and we'll need to sort of start drilling new producers in order to keep that production going in the reservoir. And so the question is, where do we drill those new producers? At some point, we'll need to start abandoning the field. It's no longer becoming economically viable at some point, and so we have to plan that. And that means we have to answer the question of when should we stop production. So what you notice here in this kind of management decisions that we are asking very simple question, which is how much water to allocate, where do we drill, and when do we abandon the field. So we should not lose track of this fact that essentially what we're trying to predict are very simple things. Of course, in this system, we can't really, over this example, we can't make any future predictions without building models, simply because the information that we have is quite heterogeneous in nature and also very sparse. So when you build models in the subsurface, whether you have deal with groundwater or heat or storage, there are typically a number of things to consider. First is that there is a large-scale sort of variation, which is due to the structure. It's the fault and the layering, the horizons, the contacts that we have in the system. Within those structures, then we have rocks, which is described by petrophysical properties, and these could be varying. For example, the common would be porosity, permeability, but also when we are going to integrate seismic data, we have to worry about other types of geophysical properties or rock physical properties, such as the velocity, density, and impedance. If we have fractured systems and there's issue with compaction or changes in stress that have an effect on the pores, then we also have to deal with geomechanics. And then the third, within those rocks are fluids, and those fluids have their own properties, particularly when you have multiple phases, when you have oil, gas, water, or different kind of water, salt water, non-salt water, etc. They have their own properties. And so what we're seeing here is that that we're going to build very complex models, or probably needing to build rather complex models, and that these complex models have all their own fields of study and understanding. But in the end, what we need is uncertainty quantification that leads us to what was on the previous slide, is try to understand and answer very simple questions. The second case study has to do with groundwater management in Denmark. So here we are in Denmark. So is a map here of Denmark, where you see some, here we're in Denmark, where you have the city of Aarhus, where you have a pretty small area there where people would like to plan for a new drinking well field. And these 4 locations are being offered as an alternative for that drinking water field. So the question is, which of those 4, A, B, C, or D, will we be choosing one of these alternatives? So to come to the decision, of course, we have to again make predictions. Groundwater systems is even more complicated than oil systems, simply because we have an open system now, so there are boundary conditions to worry about. When you start pumping, you may get contamination, drawing in contaminants from agriculture or industrial areas, so you have to worry about that. And so increasingly, therefore, in groundwater management, we're taking more and more information that's high quality. For example, here at the bottom, this is geophysical monitoring by means of SkyTEM data. This is basically EM data that then can be used to monitor or determine the resistivity in the subsurface. And so this resistivity will be indicating something about the heterogeneity of the subsurface. If we notice already, it's quite heterogeneous in the sense that we seem to have these channel-like features, and these are, we'll see in the next slides, these are essentially the glaciated features, old buried valleys that have been filled up with gravel and shales. So that's what is shown here. This is a conceptual picture. This is not an actual model of what is available, and see a very complex intersecting of several buried valleys. There are glaciating periods, and even those, they're filled with gravel. Even in those, we have heterogeneity that could be sands or clay. Those are essentially some of these brown channels here are clay channels. In some of the red channels with the sand, we have some clay features. So again, we have a decision to make. We have 4 alternatives, but we have also a bunch of objectives. And often what we'll see is that there is sort of a risk versus return that has to be made. And this is true for all the case studies. The risk here is that when we start extracting water, that we'll get contamination. And contamination is something we'd like to avoid. One of the reasons for carefully choosing these well fields in Denmark is that they have observed that groundwater extraction may cause wetlands to be drained or may affect stream flows. And so they would like to reduce that effect. And so that would be a return then. Once we can maximize that reduction and maximize that increase, we'll get a return. So we have to balance all these various objectives with each other, and from that balance we have to take our best alternative. And so we'll at some point make a table that lists the alternatives versus the objectives, and then from that we'll start making decisions. The problem, of course, is that everything is uncertain. We don't know exactly what the stream flow reduction is, or the outflow to wetlands is, or we don't know exactly what the risk of amount of contamination is going to be. So all these are subject to uncertainty, and again, we run into a problem of decision making under uncertainty. Third case study has to do with contaminant remediation in Colorado, and particularly the uranium contamination due to stockpiling of uranium ore waste that's due to the weapons fabrication. This is during the Cold War. And so here we see that some of that stockpiling of waste was done next to the Colorado River. So of course, after a while, because of the rainfall, because of the leaching in the subsurface and the fact that the uranium becomes mobile, there's a risk of contamination of the Colorado River. And that's something that happens throughout the United States, and something that has to be dealt with. And one way to deal with that is to treat this area. We can't just remove the entire area. So what is often done is to inject a particular product in the subsurface, in this case acetate. This acetate then enhances microbial activity, which then allows to reduce the uranium, and thereby from uranium-6 to uranium-4, and thereby immobilize that. So the question there is this efficient? So here is this idea of injection, and to assess that efficiency, they have created essentially some monitoring wells. And so monitoring wells, you would measure concentration of uranium or sulfate or other kind of species, chemical species. So the question is, can we deduce from all these measurements the degree to which we actually get reduction of uranium-6 to uranium-4? And that's essentially the picture we'd like to know here, is that do we see something rather, this is a concentration of that uranium, do we see high concentration of uranium, or do we see uranium actually escaping the system? And we'll see in the application and throughout the course that geological heterogeneity is an important factor here, and so we have to understand that, and these monitoring wells will allow us to help and understand that. Again, we have many uncertainties, so we'll have to build models, models of the subsurface. Aspects of these models are hydrogeological, such as hydraulic conductivity, but there also be, of course, because we are dealing with reactive transport, we also have to understand reaction rates, in particular geochemical properties of the subsurface as we inject this acetate and enhance microbial activity. So the complication is here again in the model, and also how we can reduce uncertainty in those model parameters using, for example, in this case, that monitoring data. Another example is that of shale development, where now uncertainty is essentially very different. Here, uncertainty quantification is very different because here we'll rely less on mechanistic models, let's say, such as mud flow, crunch flow, eclipse, but more and more on data that is being obtained at a very high rate. So our uncertainty here is data-driven, and our models are more statistical, or sometimes the word machine learning is mentioned as well. It's basically the same thing. It's we're going to build sort of statistical models that allow us to make those predictions. So the uncertainty is, again, an issue. So even though we're only going to use statistical models and not, say, flow models, the complexity of the modeling is still there. What we'd like to predict, of course, is oil and gas rates. And our controls is that is basically what's called completion. That means how we drill, what kind of fluids we inject, and how many stages of injections that we have. And then we, of course, have the geological factors and the fluid factors that are involved, just like in the conventional system. So again, we have large, complex model with several uncertainties that now have to not be learned from mechanistic or causal models, but from the data itself. Regardless of this complexity of the model and the uncertainties, often producers would like to understand very simple questions. They like to understand what geological factors were most important so that they could optimize their production. They'd like to then, once the production starts, like to again predict and quantify uncertainty on production from such wells. They also like to understand how confident we are about those, given the limited amount of data that is there. So if you have a data-driven method, then you have to worry a little bit about how much data do we need really to confidently state that statistical model and for data scientific methods to be applied. So what is now, we have looked at a number of cases. There's also the geothermal case, which is described in more detail in the book. So what is common about all these cases? And I'd like you to, before going to the next slide, I'd like you to think about that a little bit. So think about what is really common in all these cases rather than what's specific. Simply because it's easy to start focusing on really the details and the specifics of each situation. And that's often what we also notice in literature, is that the groundwater literature is very different from the petroleum literature. It's very different from other literature, minerals literature. And so it's good to understand the commonalities and synthesize what we have discussed in the previous lecture, in the previous slides. So take your time. Okay, if you have taken a little bit your time, you will notice that in each case, first and foremost, is to think about a decision problem. It's easy as a scientist to start about modeling and say, we have a model and we need to calibrate a model and we're getting information and we need to understand the nature of the information. It's important to start framing everything within a decision problem. And we noticed that in all the case studies, there was such a problem. Sometimes the decision problem is to whether we should be getting data and what data we should be getting, where we should be drilling, when we should be drilling, how much we should be extracting and at what rates. Should we actually go ahead or we just walk away or do just absolutely nothing? And that was true for all of these case studies. So there's also no future prediction without building models. I'd like to, sometimes models are overemphasized, I feel. But if you're going to predict future, you can't just use data. And even if you use data, you'll have still to build some kind of statistical model to do any future predictions. Now, in most of our cases, certainly all the cases except that shale case, we'll be building physical, chemical, biological models. And so in building the models, we should not, again, go ahead necessarily in building extremely complicated models. We'll build the models to predict certain important decision variables. And that's really the purpose of building models. It's not just building models to do a modeling exercise. And therefore, we need to understand what is impacting those important decision variables, and that will be then the sensitivity analysis that we'll be discussing throughout the course. Models are important, but data is, of course, equally important. We're going to use data not so much to constrain models perfectly, but to start reducing uncertainty. The goal, again, is not to reduce uncertainty in model parameters only, but is to reduce uncertainty in those predictions we'll be doing from those models. And so you see how that we're refining this problem now from a decision problem to a prediction problem to a data problem. And we'd like to understand what information is most useful for that. Is it drilling? Is it geophysics? Is it a combination of things? And that will be the value of information question that we'll be addressing. You also notice that there are common challenges in all these case studies, is that our models are relatively complex. In subsurface to deal with, we have to deal with structure, with rocks, with soils, with fluids, with reactions. The data that we have is very heterogeneous in nature. The variety of data, that's what that means. We also uniquely have to deal with the geological component of all this, is that geological information is qualitative, but we have to somehow turn this in a quantitative fashion for it to have any kind of influence on the decision problem. We'll see that computation time is going to be an issue. If we're going to run things like reactive transport models, then these can take several days, several hours to days sometimes. And so we'll have to worry about the amount of models that we create and how we use that information in an efficient manner to mitigate the computational times. So in the lectures that you will see there, we'll talk about exactly in the same fashion as before. We'll talk about decision-making under uncertainty. So that's decision science and decision analysis. Then I'll give a broad overview of how we are all going to put all this together, namely a method, or not a method, an approach or way of thinking about the problem is called Bayesian evidential learning. And so here you recognize the word Bayesian. So we'll be using a Bayesianistic method. Evidential would refer to that we want to use data. And learning is that we're going to use data scientific methods in Monte Carlo in particular to start doing this in an efficient and manageable fashion. I mentioned already sensitivity analysis. Understanding what impacts what is going to be extremely important in making this an efficient exercise. Data will be used, models will be used, so inverse modeling will be very important. And there we have to worry about, in particular, the geological aspect of these models. Namely, we're creating models that somewhat need to be geologically realistic. There will be also methods where we mitigate the whole inverse modeling complexity, and we'll do direct forecasting. We're talking about updating models when we get more information, and also we're talking about the mitigation of the computational issue by surrogate modeling. I mentioned value of information as an important part, and also data-driven methods, and that will be the Shale case. So there we will be less using physical, biological, or chemical modeling, but more statistical models. And then we'll, of course, have several case studies that we'll come to at the end that will be presented. So there's two textbooks we'll be using. Of course, there's the Quantifying Uncertainty of Subsurface Systems. That course really follows closely a lot of material in there. We won't cover all of the material in that book. It's quite substantial. Just kind of focusing on what your needs are. Then there's also the book by Eidsvik and Mukherjee about value of information in the earth sciences. So that talks a lot about decision analysis, and value of information is really complementary to the uncertainty book. I mentioned that there is video material, and so if you subscribe to the channel, you'll get notifications of new material that's uploaded, and next to this course you'll find other course material as well as tutorials for various software. There's a bunch of software that is publicly available as Jupyter notebooks, which allows you to, say, run through these examples. It replicates some of the case studies done in the book, so that allows you to understand what's being done and also possibly, say, use your own data and run some of these methods.